Well, welcome everyone to geohug. So before we do kick off today's session, I would like to take this time to acknowledge the traditional lands which we're all coming from today. I live on the beautiful lands of the Gadigal of the people of the Aurora Nation, and I'd like to pay my respects to the elders past, present, and future. And yes, I am so happy that we have David Drejing-Carroll joining us today. So David is a principal geologist in the project generation group with Boliden Mines, based in northern Sweden. So in 2011, as project geologist, he led the discovery of the Nautanen North copper-gold deposit, where ideas regarding iron oxide copper deposits began to take shape. So it is going to be absolutely brilliant hearing from him today about the discovery history and geology of this deposit. So thank you so much, David, for joining us today. It's amazing having you here.
No worries.
I was very curious what got you into geology in the first place?
Yeah, I was thinking about this after you asked. My father, he was a geography teacher, and so I got a lot of exposure to like physical geography and the natural world growing up. And then I did my college in the UK before going to university, and I was lucky enough to have a local college that offered geology as an A level. So I did 2 years of geology there and had an amazing teacher called Mr. Whiteman, who sort of inspired me to become a geologist and study more. And it's kind of thanks to him, I think.
That's awesome. Oh, it always is that like personal level. Like if you have someone inspiring that you know that's in it, then it really helps get you into it, I think. Yeah, that's so cool. And you've traveled a fair bit with your career. I was curious, like some highlights, some of your favorite geological locations. Yeah, any big standouts for you?
Yeah, I was lucky enough to join Randgold Resources in 2010, I think it was, just when we were making the discovery of Brincoto, this giant orogenic gold deposit in western Mali. So I was part of the team drilling that out and delineating it for 18 months to 2 years and putting it into production. And that was like really cool. Mali was an awesome place to work, amazing, friendly people to work with, and some brilliant geologists. And it was incredibly intense. We were working like 13-day weeks, and we were based there. So we got exposure to a lot of the typical studies, scoping, pre-feas and feasibility within a year, and then putting things into production. So it was amazing in that regard. Yeah. And then, of course, coming to northern Sweden and working on deposits in Norrbotten has been really cool as well. I've enjoyed that a lot.
Yeah.
Fascinating geology.
Wow, that's amazing. And have you collected any amazing pet rocks on your journeys?
Yeah, I dug out from my cabinet, like my pet rock. I can't find my favorite one at the moment, but I do have one that I have with me today. And it's this, I hold it up, try and get it on the camera if it doesn't blur off. And it's like, it comes from the old mine of Nautanen that we'll talk about today. And it's a beautiful, you would just describe it as a geologist, you would probably describe it as a metamorphic rock. It's this beautiful biotite schist with these porphyroblasts that just pop out of garnet. And then it's got on the backside some veins of what appears to be scapolite and other minerals sort of crisscrossing it as well. And it's waste material. It comes from the waste dump of the old mine, and presumably it's adjacent to the high grade copper they were mining there in 100 years ago. And what we know now is actually it's not really a metamorphic rock. It's a metasomatic rock. It's an intense potassic calcic altered rock with a bit of sodic alteration there as well. And in places you can see some of these porphyroblasts having they've got poikioblasts and entrails of chalcopyrite entrained within them, and it's just a beautiful rock, I think. And it's very hard to find it now. I think that the dumps have been sort of picked over, and the exposures are not really there anymore. But when I arrived there about 14 years ago, there was lots of the material, and it just intrigued me. Like, what the hell is this? What's it doing here? And what does it mean? So I've kept that since then.
That's amazing. Wow, that was really cool. Well, thank you for sharing that with us, and thank you again so much for being here today. It's amazing. Yeah, I'm really excited to learn all about this deposit. So yeah, thank you. And yeah, if you want to share your screen, we'll get stuck into it.
Okay, so I'm going to talk now about Nautanen North, and the title of the talk is a geology and the setting of a Swedish iron oxide copper gold deposit. And before we get into the bulk of the talk, I'm going to just make some acknowledgements. And firstly, to Boliden Mines, the new Boliden, they just a bit of a disclaimer. They're my employer, have been for 13 years, and they've sponsored the research work on Nautanen and sponsored my PhD, and they've supported the exploration work since the discovery and given it space to grow, given it space to develop new ideas and to test new ideas. And it's been really productive, and it's been a fun place to work. And then I'd like to acknowledge ICRAG, the Science Foundation Island Research Centre in Applied Geoscience, based in UCD in Dublin, for facilitating the research, the bulk of which was done at UCD, with components undertaken at Trinity, and then other components that I won't be talking about today, done at GFZ at Potsdam, University of Edinburgh, University of Lund in southern Sweden, and a little bit of the work sharing today was done at the University of Alberta as well during COVID. Of course, it's important to acknowledge the exploration team in the IOCG group there, from the discovery until the present day. There's been a lot of people and a lot of eyes have looked at the deposit over that time period, and everyone sort of brought fresh ideas and fresh interpretations and shared quite openly what they're seeing when they're looking at these very complex rocks. And then my co-authors from what I'll show today, Murray, of course, Dave Collar, Sean Johnson, Danny Hyacinth, and Robert Kieser have contributed to aspects of the research that I'll go over today. So just a brief overview of the talk. And we are going to look at the regional setting of northern Norrbotten, and then we're going to look at the local geology in the area where Nautanen North is, and then we'll dive down and we'll look at the geology of Nautanen North itself. We'll look at the timing of sulfide precipitation at the deposit and review how the deposit might be classified in sort of traditional iron oxide copper gold classification schemes. And then we'll look at the regional setting again with this fresh interpretation, with this sort of key, and review the other deposits within an updated iron oxide alkalic calcic framework, the mineral system model there. So if we look at this abstract map that Boliden has, this is where Boliden has active operations today in terms of mining and smelting. We have active mines in Sweden for zinc, lead, silver at Garpenberg, just north of Stockholm. We have the VMS deposits of the Skellefteå belt, where I'm sat today. And then we have copper, gold, and silver mining going on at Aitik in northern Sweden. And then in Finland, we have the Kevitsa deposit, this nickel copper PGE deposit there. And then, of course, Tara in the news a lot over the past year and in recent weeks. It's coming back into operation over the next couple of months, our Irish type lead zinc deposit just outside Dublin in Navan there. And then we have smelters in Norway, 2 in Sweden and 2 in Finland as well. And we're going to look at northern Sweden here in a moment. We're going to go to what we call the Aitik area in the company, and we'll look at it in a bit more detail. And we're going to look at the regional geology now of northern Norrbotten. So Aitik, the Aitik area, Nautanen North are located in the Aitik area. It's within northern Norrbotten, Sweden. And in more specific, it's located in an area referred to by economic geologists as northern Norrbotten or province. In the province, the basement is composed of Archean granitoids and gneisses underlying the sequence we see here. And it comes down broadly to the line that you see where the geology stops. After that, it's sort of a reworked Archean basement. It's thought to be there. Overlying the Archean, we have rocks that are 2.5 to 2 billion years old. They're rocks of the Kiruna Greenstone and Corvo groups, and they record this period of rifting and basin formation there. Overlying those unconformably are Paleoproterozoic rocks. They are the Porphyrite and Kiranavara groups. They're about 1.89 to 1.88 in age. They're depositing in a continental or intercontinental back arc setting. Coincident with those are these volumetric intrusions. These are the brown on the map. They're the Haparanda-sweet rocks. They're granite, quartz monzonite, gabbro, diorites, these kind of things. Also contemporaneous are the rocks of the perthite monzonite suite, and these are the more blood red on the map. They're granites, cyanites, and quartz monzodiorite also. There are broader batholithic intrusions that you can see. This is like the pink on the map. They're much younger in age. They're 1.8, 1.75 age rocks, and they're granitic intrusions of what's called the Lena suite, or further south, it's the Edefors group, Edefors suite, sorry. And of course, the region hosts major deposits, particularly of iron oxide apatite. It's the type locality there at Kiruna for iron oxide apatite mineralization. There are other major iron oxide apatite deposits at Svappavaara and down at Mount Berriet, where we'll look in a moment. And then there's VMS deposits with Viscaria sitting in just to the west of Kiruna, although I understand that maybe people are looking again at the deposit model there again. And then there are a number of skarn deposits throughout the area, a number of banded iron formation, arguably porphyry deposits, and then, of course, iron oxide copper-gold deposits that we'll look at today. There are a number of shear zones crossing the map here, predominantly with a northwest-southeast orientation, and they're active during what's called D2 deformation. It's about 1.8, 1.75 ductile phase of deformation, and then they become a bit more north-south on the western and eastern extremes there. So we'll dive in and look a little bit at the metallogenesis. When were these deposits forming? And we sort of amalgamated the volcano-sedimentary sequence, the intrusive sequence, and the dated mineral deposits or interpreted age of the mineral deposits here. And we see iron oxide apatite deposits such as Mount Berriet and Kiruna are dated or interpreted to be forming about 1.88, shortly after the host sequence was deposited or thereabouts, and just before deformation was starting to occur. There are a phase of iron oxide copper-gold deposits forming, particularly in the Kiruna area. You have Rakiau and Discovery Zone and a number of other smaller prospects that seem to be coincident with that phase. And of course, it's when the Haparanda suite was getting in place, so you have potential porphyry deposits forming, and that's broadly the age of the Aitik intrusion. And then there's not much recorded for about 80 million years, and then you go into the D2 deformation, getting ductile activity along those shear zones. Emplacement of the leaner granite, emplacement of what's called the Trans-Scandinavian igneous belt, and the hydrothermal circulation cells are picking up again. You're getting development of iron oxide copper-gold deposits during that time period, and arguably maybe a small phase of iron oxide apatite emplacement as well, at a number of smaller deposits. Now we'll jump into the local geology, and we're going to go to Gällivare. We're close to the mine of Aitik and close to the mine of Mount Berriet, and this is where Nautanen North lives. And here's our new map we've learned a lot of new airborne magnetics in the past couple of years, and obviously a lot of geochemistry from exploration over nearly a century, and upgraded it and interpreted it into a new geological map. And the oldest rocks on this map are occurring out to the east. They are 1.88 age rocks of the porphyrite group. They are mafic to intermediate volcanics, volcaniclastics, and associated sediments. And they're fitting here in this big sort of sin form where Lickevire is. And then as you move over to the west, you move up stratigraphy, there's interbedding in places, and you go into the Kirunavara group. And those are intermediate felsic, volcanics, volcaniclastics, and associated sediments. And that is sort of the main host rock to the iron oxide apatite mineralization in the area. There are a number of intrusive phases here, and the main one is sort of clipped off by the legend here, but it's occurring in the south central portions of the map. It's this big green, dark green circular intrusion, and that's Dundret. It forms this prominent hill in the region. It's a mafic, it's a layered gabbroic complex. It's occurring at about 1.89 in age. And then out to the east, you have the light browns again. It's the Haparanda suite, granodiorites, diorites there, 1.87 in age. And then in the south, you have the perthite monzonite suite, the granite cyanites, again, sort of contemporaneous in age. And it's all encased in the leaner granite. It's much younger in age, about 1.81 to 1.75. And then joining Aitik up to Nautanen is this deformation zone, big ductile shear zone. And it's called the Nautanen Deformation Zone, the NDZ. It's a zone of intense ductile deformation, intense metasomatism and hydrothermal alteration. There's a lot of sulfide and oxide mineralization associated with it. And that's where we're going to spend the rest of the day today. So just touch on the deposits that are here on the map. Okay, we've got Mount Berriet. This is the iron oxide apatite deposit. It is mined by LKAB, the state iron ore company. It's been in production for over 100 years. You see an image of it here on the left. This big open pit, sub-level open caving operation. And it's kind of a sad story. It's similar to Kiruna, where they're moving the town, but they're not moving the town here. They're sort of just closing the town down, and lack of investment for decades, as the structural instability of where all the houses are sort of becomes too much. It's too unsafe. it occurs, the deposit itself, is a series of sort of Boudinaged iron oxide magnetite and with a bit of hematite and apatite lenses that are strung out over a number of horizons within the stratigraphy. And they're Boudinaged and then folded into the synformal open fold that plunges off to the southwest. But it's got remaining reserve resources of about 1,779 million tons of 50% iron. And they're down at like 1,000 meters or so. It's quite an impressive operation. Then we have the mines that Boliden has in operation currently. We have Aitik and since the last few weeks, Liikavaara. These two open pit operations. Remaining is 940 million tons at 0.17% copper and 0.1 grams per ton gold. Very low grade for most people, but it's an interesting story because it's actually in Aitik itself, there's this high grade core running about 0.5 over maybe 80 to 100 meters or so on these D2H structures on alteration and styles that you'll see today when we look at Nautanen. It's basically identical. It's recumbent. It's dipping over to the west at about 60 degrees, and it's very favorable to mine in an open pit. And we just sort of bleed the grade out and take a lot of the low grade material. Liikavaara, I don't know the story there too much. I suspect it's sort of kind of similar to Aitik in that regard. And then we have Nautanen in the north there, 25.5 million tons at 1.51% copper and 0.8 grams per ton gold. And it's the opposite story. That's just the high grade core of Nautanen. We have a low grade halo around it. It would bump those numbers up substantially, but we don't see us mining that in an open pit operation. It's vertically dipping. There's just no way to really do it. The social license wouldn't be there, and the economic probably wouldn't work either. So we just the low grade there. And it's open still. It will continue to grow over the next couple of years. And into a bit more of the history of Nautanen. Well, at Nautanen North is our new discovery, but there was a mine at Nautanen, some 2.5 or 3 kilometers to the south of what we found today. It was discovered in 1898, and then it was in production from 1902 to 1907 for copper, gold, and iron. And they produced about 6,000 tons of ore before the company went bankrupt and things got shut down. There was a bit of exploration sort of went on after that. You see these trenches and things that were made, and nothing really happened that was sort of serious until the 1980s. And then a company called SKAB, Sveriges Geologiska Aktiebolaget, came and drilled in and around the old mining area quite tightly and defined two zones of mineralization. But they were very low grade and they were very small, and then just walked away. North Atlantic Resources came after that and did a lot of drilling along the strike of the shear zone. That was a Boliden Lundin JV. It was the company that became Lundin, you could say, afterwards. And they did drilling and then walked away again. And then Phelps Dodge, now Freeport, came in the 2000s, did some drilling, geophysical surveying and soil sampling, and had some interesting intersections near the old mine. We came along in 2009. We resurveyed a lot of those drill holes, and we sort of realized they weren't going where anyone thought they were going. There's so many competing magnetic fields in the area, and they're getting put out with a compass that maybe they were 90 or 180 degrees away from where the hole was supposed to be. And consequently, that affects everything, because you can't interpret and solve a complex geological problem if you don't really know where your data is coming from. So what did we do when we came in? Well, we got the property in late 2009, the bulk of the work starting in 2010. And we focused in the beginning on geological mapping and geophysical surveying and some top of bedrock and base of till sampling as well in the area. And we discovered this large sort of EM anomaly that you see on the right. It was coincident with this large magnetic anomaly. And we thought, okay, let's come in, let's drill this and test this EM anomaly. So we planned incredibly deep drill holes, 1,000-meter holes, to come in and test as much of the system as possible. And we started here in the south and then progressively moved north. And I was running this program and I was just seeing, 1,000 meters of drill core that I had to log with no help, and incredibly altered rocks. Didn't know how I was going to put this into the VMS logging and coding system of Boliden, and I was a bit nervous. And I was driving up to when the NAB6 drill hole was drilling. I was planning on stopping the hole and getting on with this mess. And I thought I would throw up the core that had been drilled the previous 2 days onto the table and check it. And I did that. And it was just core box after core box of very high grade copper mineralization. And the final intersection of that hole was 114 meters at 0.86% copper and half a gram of gold, with an including of 24.15 meters at 2.74% copper and 1.28 grams per ton gold. There's quite a bit of silver and moly also, but Yeah. And that's just, you know, astronomical. We don't really get those sort of grades commonly. We couldn't stop the hole, of course. We had to keep drilling and upset a few people that were on their way up to survey. But it was the final hole of our program. We went away, we logged the drill core, and then we went out to the field that summer. We did a lot of field mapping with a structural geology expert, Dave Collar, and mapped in the old mining area, looked at the alteration assemblages we could see there associated with the old mines, looked at what we could see with the structural geology, and noticed like intense potassic alteration in the old open pits, and then, you know, inflections in the dip or the strike of the shear fabric seemed to be coincident with that. And that we used as the tool, the guide, when we came back and drilled under the initial hit. Waited to find that in the drill core. The whole thing had steepened up. We knew then we had a vertical system. We saw that change in inflection. We saw the strong potassic alteration, and we got the high grade copper in the next box. And then it's just been drilling it out since then. So let's look at some actual rocks and stop looking at words. And here is a sort of the logged rock type cross section of Nautanen North, and then we have examples of those on the right, in the bottom right. And I'll start with the peripheral rocks. So we're going to look in the bottom right rock here. It's the amphibole biotite gneiss. It's dark green on the cross section. We correlate that with lithogeochemistry and map reconstruction with this basaltic volcaniclastic that we see outside the shear zone. As we come into a biotite gneiss. It's like amphiboles altered out. It's the same rock. It's just an alteration. Fasci's change. And then we come into a very distinct unit. This is the banded biotite gneiss. It's the orange on the cross section. And you get these bands or lathes of incredibly coarse biotite, like the sample I was sort of showing a minute ago, hosting beautiful porphyroblasts of garnet. And those porphyroblasts can be altered out to magnetite or tourmaline or other things. And geochemically, it corresponds with this basaltic peperitic unit we sort of see outside the shear zone. And then the main host rock, we come over a structure, we're into a sericite garnet gneiss or schist at times, has a bit of a relic porphyritic texture in places, and it correlates lithogeochemically with this porphyritic andesite that we find outside the shear zone. And in the footwall of Nautanen to the west, and particularly in the north of the deposit, we find this granite, quite mafic in this example here, but it is what would typically be called a leaner granite regionally. And it's coming up is in placing pegmatites into the system. And of course, they're alteration rocks. I'm basically describing alteration rocks just within a coding system. And we've now gone away and done all the alteration petrography, and we can actually propose alteration assemblages within sort of a modern iron oxide alkalic calcic framework now, proposed, say, by Louise Corriveau. And the oldest event that we see preserved at the deposit is this sodic alteration event. It's occurring as coarse porphyroblasts of scapolite. It can be commonly replaced by other things. It's overprinted and took away. And we can see it transitioning into a sodic calcic iron event. You're seeing amphibole, you're seeing hornblende actinolite with magnetite, with sulfides occasionally coming into the rock. And those can come in as wall rock replacement, or it can come in as veins. It's multiple events, and it's occurring during deformation. The veins can have halos of sodic feldspar, albite or scapolite, and sometimes without. It's a true sort of transitional assemblage. That transitions over into high temperature calcic iron, actinolite, magnetite, hornblende, a bit of epidote in the rock, and then into a high temperature potassic iron event. All the amphiboles are getting altered out to biotite. You're starting to see K feldspar coming into the rock for the first time. Albite can be there occasionally. And in rocks with a bit of pyrite, you're seeing sericite starting to come in. When we go over structure, we come into a pure low temperature potassic iron rock. It's dominated by sericite. There's a bit of chlorite, a bit of carbonate, a little bit of hematite. And all the iron oxides basically replace the iron sulfides and copper sulfides in that. And it's the main host to the high grades mineralization. We have a late calcic potassic iron phase that we see here. It's coming in. You're seeing these beautiful bands of K feldspar and hematite with beautiful apple green epidote. And you see it at outcrop in the shear zone. You try and map it up, and it's just chaos. It seems to be following brittle fracture networks, and it's a bit of a nightmare. And then we have a late quartz tourmaline overprint coming in as veins. It's predominantly like along tension structures, we think, within the shear zone. Does a little bit of wall rock replacement adjacent to it. And in rocks that are already mineralized, it's sort of remobilizing sulfides into the veins, but it doesn't seem to be bringing sort of fresh sulfides in with it. And then we can go back and redo our cross sections and level plans with that new assemblage. work. And we have on the peripheries, we have the high temperature calcic iron. We come in through a transitional assemblage, and then we go into a pure high temperature potassic iron assemblage. And then in the core of the system, we have this low temperature potassic iron just sort of cutting through everything coincident with that structure and hosting the high grades of mineralization. It works really nicely. And the mineralization itself, well, there are many different styles. These are some of them. We've got magnetite here in the example shown as veins with sort of halos of actinolite, and then one with biotite, which is presumably altering an earlier calcic mineral that was there, either actinolite or hornblende. It can occur also as disseminations. It's very common. In fact, it's the most common method. Every rock is just full of disseminated magnetite, apart from the core of the system where it's all replaced out. And then it also occurs within breccias as well. And then we can see some examples of the breccias in the center here. These have clasts of magnetite of earlier sulfide phases of pyrite, pyrrhotite, and then clasts of altered wall rock, including low temperature potassic wall rock, is also mineralized, and it's entrained in that. And then it's encased in a matrix and cement that's predominantly composed of chalcopyrite with tourmaline in places. You see beautiful grains of tourmaline under the microscope there. And it transitions out laterally into veins. And you see these on the right here. You see again, predominantly chalcopyrite as the main vein fill, with a little bit of tourmaline, and then magnetite, pyrrhotite, and pyrite can be in there as well. And they're getting replaced progressively there. Most of the magnetite's normally gone. And then there could be sporadic molybdenite throughout those veins as well. At depth within the deposit, we start to see sulfates coming into those veins, getting anhydrite and fluorite and other things coming in there as well. If we look at a pseudo section where the mineralization styles are, and we start in the west, we see disseminated magnetite sort of along the primary or original sort of S0, S1 fabric of the rock, and then it's getting entrained and sheared out by S2 shear zones, and then as it's getting wrapped into the system, it's getting replaced to iron sulfides and copper sulfides. On the east of the system, we have these high temperature calcic iron veins. They're hosting magnetite with sulfides also. And then in the core of the system, you're getting high temperature potassic iron alteration rocks, and they're hosting stockworks and micromesh networks of sulfides and occasionally uraninite and other things. And then that's where the breccias are also sitting, in the core of the system. And then on the peripheries, we start to see the veins a little bit more. If we just map up the grade halo of the deposit, and we take a low grade halo, anything above 0.1, and a high grade halo, anything above 0.9, we can start to see this inflection in the high grade that is common. Things steepen up and sort of overturn back on it itself. And we can trace that in the serial section north and south through the deposit, and it appears to culminate in the center or south center of the deposit in this culmination. We interpret that to be this antiformal culmination. Everything's dipping off, and it's formed in response to reverse sense of shear, like inverting that structure and thickening up and doubling in places the grade and the width. If we look in plan view at it at a number of different levels, we see these sort of large high grade zones forming in response to inflections or changes in the dip of the shear fabric. And then we see moderate and low grade mineralization sort of splaying off these controlling shears and propagating out into the wall rock. It's like a sort of, it's an orogenic deposit essentially. In the north, we have a lot of orientated drill core. So we were able to map up these high grade breccia zones and shears and relays. And we were able to see that they're sort of relaying over from one controlling shear over to the other as a series of stacked relays. And presumably that's forming, the interpretation is that's forming in response to reverse sense of shear on that controlling western structure. And then we see like the moderate and low grade mineralization, like I said, propagating out into the wall rock on subordinate shears. We can also look at Nautanen in terms of its geochemistry. And we can do that using the alteration iron oxide copper-gold diagram. And I was using this diagram since it was published, I guess, and it's in IOGAS for a long time. And I was just hitting classify in IOGAS and wondering then why some of my most altered samples were plotting in the least altered field, and not really understanding why that was. And kindly Louise sort of sat me down and taught me how to use the diagram properly. And that is through the use of what are called molar barcode plots. And these are day. So you take your samples, these are all samples from Nautanen North, and you calculate out molar proportions of sodium, calcium, iron, potassium, and magnesium, and plot them up as barcodes onto the graph. And then you look at your least altered rocks, your protoliths or whatever, and you see what their barcodes look like. So you then start to think, okay, I'm differing away from my prodolith, my least altered. Then I can start to think something about the history that sample has been experienced. And we also know the paragenetic sequence because we've worked it out on the microscope. So the earliest event we know to affect Nautanen or to the region is this sodic alteration event. And it shifted presumably rocks that were deposited in place with their least altered sort of chemistry, strongly sodic alteration to those, and shifted them towards the sodic end of the graph. And then it transitioned into a calcic potassic iron event after some time, potentially, and it shifted everything back again. But it wasn't starting from zero. Of course, it was starting from incredibly sodically altered and tried to move it up. But those samples were retaining evidence of that sodic alteration in increased sodic proportions on the molar barcodes. And then it's transitioning up into a pure potassic iron dominated event, shifting samples up towards that there. And then, of course, our most altered rocks, they did everything. They sort of went towards the sodic end, and they tried to get all the way to the calcic end, and then they tried to get all the way to the potassic. And in the end, they landed probably bang in the middle, where the least altered field was. And we see that when we look at the same samples with the copper footprint, the metal footprint, and we see samples occurring in that least altered field with 50,000 ppm copper, incredibly enriched in copper. So those are the most altered samples actually at Nautanen in many respects. And it taught me that you shouldn't just hit classify an iogas and think your job's done. You have to really think about the history of the rocks, the sequence of hydrothermal activity they've been exposed to. You can't just plot up potassium and sodium and have things plot in the middle and say they're not altered, because it's not how it works. You've probably got incredibly sodically and potassically altered rocks there. We can also think about where Nautanen might have sourced its copper from. Average crustal abundance of most normal rocks in the world, 25 to 100 ppm copper. There are exceptions. I don't think any of them really occur at Nautanen. So anything with below 25 ppm is, we can say it's likely depleted in terms of its copper content. And those are the dark greens on the map here and on the graph. And they sit predominantly to the east of Nautanen in the high temperature calcic potassic altered rocks and high temperature calcic iron altered rocks. So our interpretation is that those rocks have been stripped of their copper content. They've been depleted in copper. It's been remobilized and mobilized onto structures. And then it's found that structure there where the low temperature potassic iron alteration is, and it's been fluxed out. It's been scrubbed out and deposited either through structural means or through chemistry. It's like a redox trap as well, forming the deposit of Nautanen itself. And of course, the depletion cells of these systems are incredibly huge. Like, finding the deposit is the hardest thing. It's the smallest thing. The depletion cell, it's massive. You can see this in the regional data sets I have available to me. You can work it out with a copper over scandium indice. You see exactly the same thing. So we tried to date some of these phases, and we haven't published this yet. We're sort of we're revising it for a resubmission, and we tried to date molybdenite and chalcopyrite using rhenium osmium, and we got some ages. And here we put the ages into like the regional context with published hydrothermal and mineralization ages from other deposits in the area, and then of course the previously mentioned igneous tectonic history of the area's sedimentary history. And the oldest event we were able to date at Nautanen is occurring at about 1.82. It's in this high temperature calcic iron alteration. It's molybdenite in that. It's occurring with chalcopyrite, pyrite, and magnetite. It's coincident with the intrusion of doleritic intrusions in and around the Aitik area. It's also coincident with ages obtained from Gruvberget, which is sort of the next active mine to the north along the NDZ, where it's interpreted to be metasomatic or metamorphic overprinting event on titanite there. And we're interpreting that's one of the initial phases of hydrothermal fluid flow along the NDZ is starting up then. And then the next stage we were able to get is from this high temperature potassic iron altered rock. It's about 1.788. It's bang in the middle of D2, M2, and it's in the middle of linar granite emplacement. It's coincident with hydrothermal ages sort of occurring in Aitik, and also hydrothermal ages that have been worked out from the old mine of Nautanen as well. So again, another phase of hydrothermal fluid flow along the NDZ at that time, likely in response to the Lena being placed. And then we have the breccias, and they're all forming between about 1.77 and 1.75. It's probably reflecting a change in tectonic regimes from ductile towards a brittle style. It's in the waning phases of linar granite emplacement. It's overlapping with the hydrothermal ages from Aitik that have been reported, and also hydrothermal ages from Gruvberget, again to the north. And it also corresponds to some unpublished ages of molybdenite from the old mine of Nautanen. And then we have a very young event in this banded biotite gneiss, and it's coming in about 1.72. It's coincident with some ages, rhenihosmium and hydrothermal ages from Aitik, and also pegmatic ages from Aitik. And in that deposit, it's interpreted to be related to distal granitic emplacement in Norrbotten. So likely another phase of hydrothermal activity along the NDZ in response to an intrusive event in the region. So you have this story where it's like a multi-episodic scenario. It's every time an intrusion comes in, the hydrothermal circulation cells are picking up, fluid flows occurring along the NDZ, and it's forming hydrothermal alteration, depositing sulfides and upgrading the deposit. It's not a one and done, it's a true multi-episodic deposit. And how could that look like if we take a very broad, simplified overview? Well, if we go back to when the rocks were getting deposited, about 1.8, probably, well, it must have been occurring in basins. These rocks were deposited and preserved in basins. And then Mount Barrier was emplaced. And it's a massive deposit. And I interpret that there is probably a distal hydrothermal impact of that deposit's emplacement onto the NDZ, or there's other iron oxide apatite deposits closer to the NDZ that haven't been found to date. And it's producing iron metasomatism along the NDZ and the initial phases of sodic and calcic alteration there. And it's sort of coincident, these first two are coincident with one another, and it goes into a phase of early inversion and deformation. And then nothing's recorded for about 80 million years. D2 deformation starting up, you're getting emplacement of gabbroic and doleritic intrusions into the Aitik area and formation of the lignite granite. Your hydrothermal circulation cells are starting up again. You're remobilizing magmatic, meteoric, whatever fluids into those shear zones. They're stripping rocks of their copper content, of all their metals, and depositing them with hydrothermal assemblages and to form the deposit of Nautanen North, and presumably the deposit of Aitik that we mine today as well. So how do we do in sort of a traditional iron oxide copper gold classification scheme? Well, I tend to refer back to the senso stricto classification schemes of Dave Groves and co. from 2010. And they proposed 6 criteria to be classified as a senso stricto iron oxide copper gold deposit. And these are they. So I'll just go through them. We've got to have copper and gold as economic metal as well. It's a very economic deposit, and it's dominated by copper and gold. You've got to have hydrothermal characteristics, structural control, and be commonly occurring with breccias, and that's basically what I've described today. You've got to have a lot of iron oxide or iron silicates, and we do. We tick both of those boxes. Light rare earth enrichment. I haven't talked about that today. There's a lot of apatite in the system at Nautanen, and my former colleague, Margareta Medfut, wrote a brilliant paper on the apatite chemistry and age dating of the apatite, and we do have enrichment of rare earths also. We're low in iron sulfides. We're rich in iron oxides, we're low in iron sulfides. You go from Nautanen to any sort of porphyry deposit like I tend to do nowadays, and it just doesn't compare at all. We're very low in iron sulfides. Lack abundant syn sulfide quartz vein. We don't have syn sulfide quartz vein. It doesn't exist at the deposit. And depletion in SiO2, kind of hard to do, but you could argue there's a little bit of depletion in SiO2. And I've shown temporally associated with magmatism. We're temporally associated with multiple phases of magmatism, and we're not hosted by any sort of intrusion. We're not an intrusion hosted deposit here. How might we do, say, in recent sort of classifications of iron oxide copper gold by Roger Skiro, like with the iron oxide copper gold IOCG cube? Well, Nautanen, the old mine, was actually used by Pat Williams in 2010, and that work was recently republished in 2022 to help define magnetite group iron oxide copper gold deposits. And I agree with that classification, bang on the money. And Nautanen North is, in my opinion, identical to what you see in the old mine of Nautanen. If you spend a year going from Nautanen to Aitik and trying to find magnetite at Aitik for a study on magnetite within the district, you'll be struck by the lack of magnetite in Aitik. It's very hard to find good magnetite. And I know now it's because it's all been replaced to iron and copper sulfides. And then you start to think, well, maybe Aitik could be classified as an iron sulfide copper gold deposit. It could straddle that boundary between the two. And I think that goes quite a long way to maybe explaining this controversial or convoluted deposit classification. So if we want to split them up, maybe Aitik's the one to split and take a look at, and someone can write a paper and see if it holds water. So in the economic geology paper we published last year, we looked at our alteration assemblages we were able to define in Nautanen, and looked again at the published literature and looked to see what was defined in the other deposits in the region and tried to fit them. And since then, we tried to fit them into this iron oxide alkalic calcic framework, this mineral systems based on the alteration fascists proposed by Louise Corriveau and others. And we see we can actually fill up the spectrum quite nicely. We have components of deposits, say like Liquivar, it's just gone into production, where you have a lot of tungsten in the system. It's probably, was it some sort of tungsten skarn, but it was overprinted by a later copper event, because certainly the copper I've mapped in that deposit is occurring on D2 structures. And then, of course, have the iron oxide apatite deposits, Kiruna, Mount Barrett, and Charioki. You have the rare earth rich ones like Pergea recently in the news with LKAB. Would like to know what the rare earth elements are, but we'll wait and see there. And then you have components of ITIC, Salmieri. It's a satellite deposit. It's looking like a high temperature calcic potassic iron hosted system. And there are others that are cobalt rich. And then Nautanen and ITIC fall nicely into a high temperature potassic iron or a low temperature potassic iron classification. And of course, this isn't one and done sort of system. This is multi-episodic as well. This is happening over the entire span from emplacement of the iron oxide apatite deposits at 1.88 to the final emplacement of the iron oxide copper-gold deposits at 1.725 or something like that. And you get overprinting, so multiple alteration assemblages can occur at a single deposit. It's a bit, you have to use it with a bit of caution, I think. So just to finish off, Nautanen sort of meets all the criteria to sit within the iron oxide copper gold family. Sensu stricto classification, it's probably like an orogenic type iron oxide copper gold deposit. It formed in a multi-episodic manner. We're seeing that with the rhenium osmium work we're doing, and we're seeing that it's likely relating to repeated intrusive and deformation events in the area. And then using those alteration assemblages, we're able to define it at Nautanen. We can go back, look at the district and update the mineral system and sort of fill in the missing components nicely, and maybe use it as a bit of a tool to go explore alongside the cube. Yeah, I'll be happy to try and answer any questions anyone might have. That was a brilliant session. So thank you so much, David, for joining us. It's it's been awesome having you on today. So I'm very grateful for your time. Thank you very much for having me. Thank you so much. Thanks, everyone.